Physics, physics, physics. Yeah, you do.
I do it at home.
What classes do you have tomorrow?
We have before math, okay? We have before math.
What class do you have tomorrow?
You.
What time?
9.
9. Only one.
Just 1 hour at 9? And then you're finished?
No, I have
No.
a tutorial and
And the chemistry.
maybe we have chemistry, but close to nothing to us until today.
Yes.
I think you might, because I had to make a Moodle page for our new chemistry teacher.
We can start
After the holidays. We just want to meet. Not
Oh, we just have fun, like party and
yeah.
Be
What?
quiet, please.
What?
Okay.
Easter, where's my egg and where's my
I'll get you
chocolate?
some tomorrow.
Yes. What?
Oh.
Egg.
Maybe I'll have a little present for you if I can find them cheap enough. If I can find them cheap enough.
Egg chocolate.
I take it home.
I don't like that.
What?
I take it home.
We want the right one, not cheap. Big size.
You'll get what you get.
No! Can we eat rabbit?
Oh,
Dude,
shit.
stop being weird, please. Write this down.
I did.
Okay, ready?
Einstein.
See, they're talking and they didn't write anything. I did. I'm the only one there.
You're talented. You can both write and annoy me at the same time. Congratulations.
Electron.
E equal
Yeah,
MC as well. Oh.
Today, yeah.
It's electric.
No.
What are you mumbling about? Okay, continue, got that?
Yeah.
Yep. Okay,
I can't believe you told that.
right. Because the mass of a proton and a neutron are so small, we sometimes don't use kilograms because that's too big of a unit. Instead, we use a different unit for mass. Do we use grams? No, because even grams are too big. So we use this unit called the atomic mass unit, or the AMU. And what's the definition of an AMU? The symbol is a U, or AMU, and 1 AMU is this much, which is quite small.
Is it measured by
It could be. I'm not sure how they arrive at this.
so why we call it offering?
Atomic mass unit, because you use it to measure mass of atoms. You know?
You need to memorize this.
It's not
It's on your calculator.
Oh.
Look at value U
You
or AMU.
17.
You got it? Here, let's have a look. Shift 717. Yeah, there you go. You have it there. Okay, continue. Yep. Note, the mass of 1 proton or 1 neutron is about 1 AMU, but in fact, it's not exactly 1 AMU. We'll get to the values later, but just roughly, it's roughly 1 AMU. Right, consider the following nuclear reaction. We have a hydrogen and a lithium, and we fire the proton at the lithium. And what happens? We get 2 alpha particles. Is this equation balanced? Well, let's have a look. How many protons do I have on the left? 4. And on the right? 4. And how many nucleons? 8. And on the right? 8. And how many neutrons? 4 and 4. So everything seems balanced. Now, the masses though, the mass of hydrogen is 1.007 AMU. Okay. The mass of lithium is 7.016 AMU. And the mass of an alpha is 4.002 AMU. So what I want you to do, very quickly, is tell me what is the mass, total mass here on the left. What's the mass on the left here? Write that down. Yeah?
8.004.
No.
8.023.
8.023.
8.0.
Yeah, calculated
Yeah.
8.023.
Which one?
Last one.
Last one.
Oh,
The left.
simple math.
Yeah, S equals
This
to
plus this. Ah! Now, what's the mass on the right, students?
4.02.
No,
8.004.
It's not equal.
Yes, it is not equal. The mass on the left was 8.023, and the mass on the right is 8.004.
So?
That's very big because it means you had more mass at the beginning than at the end. Now,
Because it lost weight.
How do you know
yeah,
that?
but even if it loses weight,
Exactly.
but there's nothing missing from my formula. Because if I add something in here, it's not balanced.
Because it's in real life, so
No, but even in real life, if something lost mass, it has to lose it by releasing something.
Oh,
Yeah.
I got it.
quantum
Quantum.
yeah.
No,
That's right.
Quantum
No. Nice try, and not quantum physics, okay? So, what's going on here? You remember when I said, no, not heat, well, it could be heat. Remember what I said here for the conservation? The nuke, not quite disappeared, nucleon number is conserved, the charge is conserved, you know, what else did I say is conserved? The momentum is conserved, and the energy is conserved. But I never actually said the mass is conserved. The mass appears not to be conserved here. The mass does not disappear, or can it? So actually, what is happening here is there must be something missing.
Energy.
It's going to be energy, yeah. Walton, this experiment was done by Cockcroft and Walton. Now, they did not decide to do this experiment one day. You know, they didn't wake up one morning and said, let's fire a proton at some lithium and see what we get, okay? What they were doing was trying to prove a formula suggested by Einstein. Einstein predicted that when atoms combine in a nuclear reaction, some of the initial mass appears to be lost. In fact, it's not lost, but rather it's converted into energy. So Einstein suggested that the mass which appears to be lost is actually transformed into energy. And you can calculate how much energy you get. Einstein said that the amount of energy produced is equal to the mass loss times c squared. This is Einstein's formula, E equals mc squared. Oh, you want the statement? Sure. Yeah.
Do we need to write this down?
No, but Monica wants to, so. Now this is a big deal, because remember we said conservation of energy means energy changes into one form, from one form to another form. So we have electrical energy, light energy, you know, all this type of stuff. So that means mass must be a type of energy. Because if mass can change into energy, and energy can only change its form, then that means mass must be a form of energy. Mass is one of the forms of energy.
So the more weight you gain, the more energy you get.
If I was to throw you into a nuclear reactor, yes.
What?
Well, the only way to change this mass back from mass to energy is, you know, I would have to fire protons at you and destroy you. Yeah.
So it only works in nuclear option, right?
Yeah. Yeah. In a nuclear reaction. Okay, continue. So, we have our famous formula here. Well, what happened to you? Nothing? Okay. So we have our E equals mc squared. Or more commonly written, E equals mc squared. Where E is the energy, m is the lost mass, and c is the speed of light. The mass that appears to have been lost.
Lost energy and lost mass, right?
No, not lost, gained energy
Oh.
as a result of the lost mass. Got that? Very good question. It's a math thing. Believe it or not, this mathematical formula he predicted comes from his theory on special relativity. And the key idea in special relativity is that you can't exceed the speed of light, and that the speed of light is a universal constant for all observers. So Einstein said that speed of light is the limit, you can't go faster than this, and it doesn't matter who you are or where you're travelling or how fast you're travelling at, the speed of light will look the same. So it's completely universally constant for all observers. And from these two assumptions, believe it or not, you can actually get this formula, which seems very strange, because what has that got to do with this? But you can actually prove it. Yeah. Okay, continuing. So, let's look back at the example we were talking about. To balance this equation, we must have an energy term here. Let's calculate what that energy is. So firstly, how much mass did we lose? We had 8.023 minus 8.004. So we lost this much mass times AMU. So this is how much mass we lost. So what do I do with this? I multiply it by c squared. What number is c, Monica, on the calculator? C0. 20 something? Is it? 28. Right, so how much energy do we have? We have this much energy. Now, I know that's very small, but that's actually a lot for an atom. It is actually a lot. Yeah? Oh, yes. Yes. Right, so that's the answer here. How much joules? Now, because this is so small, maybe we want to use a different unit. What would be a good unit? No. If we don't want to use joules, what would be a more appropriate unit? EV, yeah. Uh-oh. It's 23, isn't it? Right. That's 17 mega electron volts. 17 mega electron volts is a lot for one atom to be doing. Because remember, 1 electron volt is the energy 1 electron has when it's under 1 volt. 17 mega electron volts is a lot for one atom. Okay, let's continue.
Can I just leave in joules?
Yeah, you can, because I asked for it in joules.
What's the value for joules?
This one also is more simple.
There you go. Minus 12. Okay, continue? Yeah? Right, continue. So, let's have a look at the exact mass. So I said the mass of a proton is about 1 AMU. This is the exact mass of a proton. Okay? The mass of a neutron is this. I would like you to write both of these down. You will need them. Which is heavier? Neutron is slightly heavier. Got this? Yeah? Okay. Now.
Still,
Yeah.
we don't have a system for today, right?
No.
No.
So, we finish at 4?
Yes. Yeah.
We start the assessment support after the break. We'll work on the physics. Okay. Now.
3.
No, 4.
4.
Now, can you tell me what is the mass of 2 protons and 2 neutrons? Yeah, so 2 of these plus 2 of these. Can you calculate it? No, it's not a trick. I want you to tell me what the mass is of 2 protons and 2 neutrons.
4.03188.
Okay, do you have that on your calculator, everybody? Yeah? So, by the way, what is 2 protons and 2 neutrons stuck together? Helium, an alpha particle. It's an alpha particle. If you measure the mass of an alpha particle, you should get 4.013. But in fact, it's less than this. In fact, it's only 4.002. This is quite strange, because think about it. You have 2 protons, 2 neutrons. When they're separate, they have a mass of 4.03 AMU. But then when you stick them together, they have a mass of 4.002.
With some energy.
Yeah, but why should they lose energy? You know, like if I put this on this. Yeah, but what, in other words, yeah, no, we all understand that this missing mass has become some kind of energy. But the question is, what energy?
Electron.
No, quite.
Not kinetic.
I'll give you a clue. It's the name of the slide.
Binding.
Think about this, okay? What charge is a proton? Positive. And what charge is a neutron?
Neutral.
Neutral. So there's nothing to cause them to stick together. So to stick them together, that some energy must be spent, so to speak. That you must have to pay a price by using some energy to cause them to stick. In fact, think about this. How can I stick 2 protons together if they're both positive, but yet they stick together? Yeah, so it's this binding energy. This is an energy which holds the atom together. Now we've talked about this because remember we said, what is the force that causes the atom to decay? Do you remember? What force causes the atom to decay, to fall apart?
Decay energy.
No.
No, the attract one.
The weak nuclear force. Remember I said this? The weak nuclear force causes it to decay. But I said there must be some other force that's trying to hold it together. That's what this force is. Now what do you think this force is called?
Strong.
Correct, the strong nuclear force.
Okay.
So you have two nuclear forces, a weak one which pushes out and a strong one which pulls in. And this energy is used to hold the protons together. So 0.029 AMU is missing. This is known as the mass defect, or the missing mass. It's not actually missing. So what's happening here? We have this thing called binding energy, and the binding energy of the atom is the energy required to hold the nucleus together. This energy E, you can calculate it. Guess what the formula is? mc squared. Again, where m is the mass defect, the missing mass. That is the lost mass. Okay, this is, I need you to write this down. And then there's one more sentence.
So binding energy is strong nuclear.
Binding energy is to do with the strong nuclear force. Okie dokie.
Is it the proton and neutron all combined together?
Say again, Christy?
That is the apparent loss in mass when the protons and neutrons are combined.
Yeah, are combined together, sorry, not and combined together. Are combined, not and combined. Now, this also has a second meaning. Imagine you have your protons and neutrons stuck together and you want to separate them. In fact, it's also the energy you would need to separate them. Okay? So, the binding energy is also an energy required to separate protons from neutrons. It's actually a lot of energy, you know, it's not easy to separate the nucleus. Continue? Yeah? Okay. So, in an earlier lecture we saw the weak nuclear force is trying to push apart the nucleus. Newton's law tells us that the atom is not decaying, there must be some other force to balance this. So a counterbalance force is required, and this is the strong nuclear force. What are some properties of the strong nuclear force? Well, what do you think? Firstly, strong. Yeah, in the nucleus, and it's force. Yeah. It's a strong, attractive force which acts only inside the nucleus over a very short range. It's the force responsible for binding between protons and neutrons.
What's the difference between strong nuclear force and binding energy?
Well, it's kind of like the difference between gravity and potential energy. So, because there's a gravity force, you can have a potential energy, and you would need to use energy to lift something in the force field. Same idea here. Because there's a nuclear force trying to hold the atom together, you would need to use energy to separate it. In the same reason you would need to use energy to lift something. Me speak English. What mistake have I made? An atom, not at atom. Yes? The nucleus of an atom. Yeah. Yeah.
What if it actually does
not possible. Not possible. Okay, Jay, you're distracting me. Did you write this down?
You're doing nothing.
I know, but you're still distracting me. Okay, continue? Continue?
Yes.
Okay, continuing. So, you might wonder if there's some, I don't know, that's a typo because I already said that this is the counterbalancing force, so I should delete that sentence. I don't know why that's still there. Yeah, no, there isn't any more to do for this one. Okay, so what I want you to do as a quick question is, oh, hang on, let me just fix that so I don't forget to. Right. This is the two protons and two neutrons. They make an alpha, but there's some missing mass, which we calculated. I just want you to convert that into an energy. I want you to get the binding energy for the alpha. Yeah, so we'll do this one. So the alpha is the alpha should be 2 times 1.008665 plus 2 times 1.007, right? It should be this, but it's not. It's only 4.002. So minus 4.002, this much is missing. If I convert this into energy, what number is U? 7? 17? No! Oh no, wait. There we go. Times, and what is my C constant? 20? No, 20? 28. I'm not sure now if this is right anymore. 2 times 1.008665 plus 2 times 1.007 minus 4.002. That's the binding energy for the alpha. Now I really want to use electron volts because this is so small. .3 mega electron volts is the binding energy. 27.3 mega electron volts is the binding energy. Got that?
Here we have a formula.
For what?
How okay.
I just did it. Use the E equals mc squared formula. Continue. Previous was this. This. It is. Well, nearly. It's like 2.997.
Wait, can I do calculation?
Which one?
Top one.
I did
Uh-huh.
2 neutrons plus 2 protons minus the mass of the alpha is the defect times U.
D1 is D-O.
That's C.
Okay.
Okay, continue. Right. What is the binding energy? Oh yeah. So now, for this one here, I'm going to keep it in mega electron volts. Where's it gone? Come back.
Nice.
It's gone.
What's the answer?
That's fine. Right. Divided by every time now. Right, that's the binding energy. In the next question, I want to know what is the binding energy per nucleon? That is binding energy per nucleon. So, how many nucleons do I have here? 4. 4, 2 protons and 2 neutrons. Why do I care? Why might I want to know what it is per nucleon? Yeah, well, the previous answer was a total to hold the 4 together. But really, I want to care. I care about how much energy is required for each one to hold it together. Like, think about this. If I have energy X to hold these 2 together, or if I have energy X to hold these 3 together, well, which is stronger? The first one. Because it's the same energy, but only to hold 2 things together. If I have the same energy to hold 3 things together, then there's actually less binding energy between them. Because I have now 3 things to connect instead of 2.
You say the energy is the same, but it is not.
No, listen. Okay, listen. Imagine I need X energy to hold these 2 together. I'm not talking about this, forget about this. And I need X energy to hold these 3 together. Which has the strongest hold? They're both X. The first one, because you need X for 2, not X for 3. Okay, so now back to this. I'm saying I should divide by 4 because I care about the energy per item, not the total. Because then, if I know what it is per item, I can compare it with other atoms to see which one is more strongly held together. Yeah. Now, of course, the total will be different for each atom, but also the total per nucleon is actually different for each atom. And that's the one I care about. Okay. So here, divide by 4, it's 6.83 mega electron volts per nucleon is required. Just 6. So this one here will be 6.83 mega electron volts per. What letter do we use for nucleons? Not Z. Is it Z? Or is it A? A is for protons, Z is for nucleons? Or do I have that backwards? You do know. Is it this way around?
No.
Or it is, yeah. Z's on the top. Yeah. So it's mega electron volts per Z, yeah. Per number, if you want. Okay, continue. So, Next now is a graph. Now this graph you need for the exam, but you don't need to write all of it down. You just need to have the rough shape. Okay, let me explain it. Oh, it's A, mass number. It's A, not Z. Yeah, no, that's okay. Continuing, Chrissy, thank you. So, look here. What atom do we have if we have one here? Oh wait, no, mass number. No, actually, no, I take it back. No.
Oh shit.
Wait.
It's A. Mass number is nucleon.
Yeah, is that an A or is that on the top?
We don't use A.
We do some chemistry too in home
We
country.
have mass number.
Yeah.
It's A.
Yeah, okay. Now, what's down the bottom here? If I have, say, just one proton and no neutrons, so that's one nucleon. What do I have?
Huh?
One proton, no neutrons,
0.
so that's one nucleon. What atom do I have?
1.
Try again.
Helium.
Hydrogen, yes,
Hydrogen.
hydrogen. So, what we're doing here on this table is we're just looking at different number of nucleons. So up here is uranium-235 nucleons. Down here is things like hydrogen and helium. And this graph is the binding energy in mega electron volts per nucleon. So as we move across the periodic table, what do we notice? The atoms require more energy per nucleon to be bound together until we reach the top, which is iron. So in other words, iron is the most difficult thing to separate. If you have an isotope of iron, it's very difficult to separate it. Its binding energy is very strong per nucleon. But then once you pass iron, it starts to decrease again. Okay? The reason is way too complicated for us. But what we need for the exam is we need this mass number, this binding energy, and you need to draw a graph that goes up, peaks at iron, and comes back down. And you need to write that this is iron on the top, Fe. Okay? So, this graph, they expect you to know it for the exam. It's the binding energy per nucleon graph. Yes? Yeah, that's... it's like you're not listening to me. They don't even need uranium. I think they just expect you to have iron on it. Now, just so you know, you sometimes hear people talk about heavy atoms and light atoms. So that's where this graph comes from, okay? You see this line here at 118? If you have more than 118 nucleons, we call this a heavy atom. Basically, roughly speaking, if it's heavier, if it has more nucleons than iron, we call it a heavy atom. I want you to write mass number, energy per binding energy per nucleon. Draw a line that goes up to iron and then down.
Oh, we don't need a defect.
No. They don't. That's not for the exam.
ions are hardest to split or to combine?
Both. In other words, Lee, it's very difficult to split an iron atom, and it's also very difficult to combine two smaller atoms to make iron. Got that? Come on, it's taking a long time. I just need it. I don't need all the details. Okay, continue. So, that's your homework question. If you can take a picture of that, please. Try not to complain so much, please.
Oh, so.
Let me have it, please. What is this?
So what's interesting, I like in question number 2, you get to work out how long a gram of uranium can power a city.
Oh, nice.
Yeah. Oh, you do need to use that as part of it, yeah. So 1 gram of uranium, you know, doesn't sound like a lot. You might think it couldn't even power the city, but you'll calculate how much time you get out of a gram of uranium.
A year. No,
I know,
but how big the city?
Yeah, well, the city it's actually a small town. It requires 10 megawatts of power.
Okay.
No, like continuously.
A year.
How small? Like Dublin?
Oh, I know, 10 megawatts would be like, I don't know, how many homes would that be? Let's say a home averages a kilowatt an hour. So 1,000 homes, so maybe like 10,000 homes.
Whoa, it is a lot.
So Dublin.
No, there are more than 10,000 homes in Dublin.
Then Cork.
200.
No, 10,000 would be like,
Limerick.
No way.
No. 10,000 is like a small community town, like Tala or something. Or
What is Tala? I've never heard of Tala.
what's your Drimna? 10,000 would be like just one district of Dublin, like Drimna or Andrew. What part of Dublin are you living in? You don't know where you live? Great. Okay.
Dublin 6.
On that we'll finish.